Hi, my name is Aidan Gesch, and today I'll be presenting my research on accelerating microstructural evolution using machine learning. I'm a part of the Department of Aerospace Engineering and Mechanics, and this project is led by Dr. Hu from the same department. In this presentation, I'll explain some background necessary to understanding my project, review my experimental methods and results, and discuss the future of my project. Understanding microstructures is key to understanding the material properties in metallics, ceramics, and more. They exist at the microscopic scale, but they influence the material properties overall, such as strength and brittleness. Microstructures form when molecules align in neat formations, and grain boundaries form when these different alignments meet. On the left, you can see some examples of microstructures in an arbitrary material. Notice how the boundary changes from the initial state at the top figure to the final state at the bottom figure. Over time, the complexity of microstructures tends to simplify in order to minimize the free energy in the state of the material. This evolution is complex and difficult to study directly, but as I'll discuss later, it is able to be simulated using a computer. Ostwald ripening is a specific evolution process which I am studying. This process starts at a high energy state with many small grains. Over time, these small grains will migrate and merge to form larger, more cohesive structures. On the right, you can see a visualization of an Ostwald ripening simulation with 4 coupled eta phases. Each eta phase is independent and of a different grain structure. However, only one phase can exist at a time. On the right, you can see the compositional phase, which combines all 4 eta phases. This process is applicable to specific situations like annealing metals and forming alloys, but in this case, it just serves as a general microstructure evolution which I can apply machine learning to. As previously mentioned, these microstructure evolutions can be simulated on a computer. My research lab uses MEMPHIS, which stands for the Mesoscale Multiphysics Phase Field Simulator. It is developed by the Sandia National Lab. This is a powerful tool that takes advantage of parallel processing to greatly increase the domain size of these simulations. I performed my simulations on the high-performance computing platform available with the Alabama Supercomputing Authority. Even with all these strengths, the simulations still take a very long time to perform. This means that machine learning can be very helpful in accelerating the process. My project started with writing a custom Fortran model, which is capable of generating a large variety of Ostwald ripening simulations. This forms a rich data set which I can use as training data in the machine learning. One way that we can study microstructures is to reduce the image to a few key parameters. We only care whether any particular point is in phase or out of phase. So first we reduce the image to binary. This is what you see in the top left. Next, you can see that we perform 2-point correlation. This is on the top right. This is a measure of how likely you are to change phase as you move through the material. 2-point correlation preserves the key characteristics of the microstructure formation while ignoring the specific locations of any particular phase. By radially averaging this plot, which is what you see on the bottom left, we're able to gain insights about the 2-point correlation, including the average size of the microstructure in the original image, which is represented by the local minimum on the graph. We can also extract key parameters through primary component analysis, which is what you see on the bottom right. As they change over time, we gain insight onto how the microstructures change over time, more than we will be able to observe visually. Finally, machine learning involves taking a large set of data, specifying an input and output, and having the computer find a process that converts the input into the output. After it's done training, the machine learning model can take inputs it's never seen before and provide researchers with useful outputs. The 3 types of machine learning models I used are a convolutional neural network, a recurrent neural network, and supervised learning using support vectors. How these models work exactly is not important to this presentation, but it is important to realize that it takes a large set of training data to create accurate results where inputs are transformed into outputs. The first type of machine learning I used is called an autoencoder. My autoencoder uses 6 layers to encode an image and 6 layers to decode it. Using an autoencoder allows you to transform a large set of data, like a 256 by 256 microstructure binary image, into a small set of data. In my case, it is 16 floating point numbers, which I represent in a 4x4 grid. This smaller data set is much easier to store and work with than working with every individual pixel in the original microstructure. Additionally, the full-scale microstructures can be restored using the same autoencoder model to visually observe the microstructures by researchers. My model has great performance with low complexity phases, but struggles with higher complexity phases. This will be resolved as more training data is generated from Memphis and fed into the model, allowing the complexity of the autoencoder to increase. The second use for machine learning is predicting the evolution of the microstructure with time. In my case, training data includes the entire simulation series, but the first 80% is labeled as input and is used to train the model to predict the last 20%. The upper figure is an example of how these predictions work, and the lower figure is the average loss over time while I was training the model. The longer that the model is left to train, the more accurate it becomes, but eventually the results plateau. Additionally, too much time training on the same set of data can lead to overfit, where the machine learning model tends to repeat patterns instead of learning how they form. Like the previous example, this machine learning model can be improved by the introduction of additional unique training data, which will be generated by Memphis using my unique Fortran model. The final machine learning model that I used is for predicting one or two of the eta phases from the rest of the phases available. Like with time series prediction, it's trained on an entire data set. However, this time it uses individual frames instead of over time. Each blue dot in the figures represents a prediction from my model, where the red diagonal line represents perfect accuracy. Predicting just a single phase, which is what you see in the lower figure, gives near perfect accuracy. So we can be confident that the model is working and produces microstructure results. And this means that we can delete those microstructures from the database, reducing the size of our storage, and then restore them later using the model. However, when predicting two or more phases simultaneously, results still show that there is some learning going on as the trend follows the red line, but there are large errors. This means that we can't be confident that we will always get the right results. Now, since these results are trained on single images, we have an excess of training data. This means that results are improved probably not by feeding it more data, but by adjusting our approach. Additionally, it might be impossible to predict multiple phases simultaneously without some level of context given. Now, what are the actual applications of my project? The first is that the Ostwald ripening dataset that I generated is the first of its kind. That means besides my dataset, or besides my research project, it can be used in other material science research. Next, the process that I'm using and the machine learning models I've developed can be applied to many different simulations of a similar nature. These could be Memphis or non-Memphis simulations. If a different dataset is used, the models will have to be retrained. However, the architecture will not have to be changed. Using these models is enticing because it greatly reduces the time and memory spent on simulation. To generate just one Memphis frame, it takes about 1 CPU hour on the Alabama supercomputer. This is reduced to under half a second on an accurately trained machine learning model. Additionally, storing the results of one simulation takes about 250 megabytes, and for 200 simulations, which is the size of my data set, it takes almost 50 gigabytes. By using data reduction through the machine learning models, we can reduce this to just 30 kilobytes for a single simulation and 6 megabytes for the entire database. The future of the project involves continuing to revise these models and increase confidence in the results. Additionally, the application of innovative new machine learning models as they're developed in the computer science field has a strong chance to revolutionize what types of data reduction and prediction are possible. Once this project concludes, I will be able to use the developed models on new data sets to drive discovery in the material science discipline. Are there any questions from the audience?
Yeah, so I had a question about the autoencoder model. At least intuitively, it just feels like 16 points aren't really enough to necessarily represent these things. So have you tried experimenting with different amounts of data, like an 8x8 maybe?
I have, and with a larger grid, it produces almost perfect results. The 4x4 is about as small as I can get while still having results that make sense. I'm confident that 4x4 is enough because of how simple the images are. This would not work on a full-scale color image, but it works specifically for the microstructure data because it's just a binary image, which we are converting to full floating point for the 4x4. And then also, they tend to be pretty repetitive. So if we know that there are small dots in one area of the image, there will also be small dots in a different area of the image. So we don't need to store every single pixel. We just need to store the patterns in those 16 numbers.
You mentioned this being the first database of its kind, but have the techniques you've described been used in previous projects?
Yes, the machine learning techniques that I'm using are widely accepted and well studied. However, this is the first time that they're being applied in this nature and being combined in this way to accelerate the phase field simulations in multiple different dimensions. This is why the research is so exciting, because it can accelerate a whole discipline of work throughout material science.
I believe you mentioned using CPUs, CPU processing for your simulations. Are you planning on using something like GPUs or any other techniques to further accelerate the simulation time?
That's a good question. The scope of my project does not include using GPUs or other modern techniques to improve the Memphis simulations itself. That is legacy code that I've created a new class for to create my database, but we're not editing any of the core simulation. GPUs are something that would be useful in increasing the training speed of the machine learning models. This is something that we even see in the big tech large language models that are currently coming out. However, once it's trained once, we actually don't need GPUs because the results are produced so fast anyway.
Could you explain how you were able to use the three models in combination with each other?
Sure thing. So the autoencoder is actually what we use to create the input for the other two models. The large-scale images are much too big for any current available model, but the autoencoded small image is available to be used. And then the other two models can be used interchangeably. We can take inputs and outputs of any size. So you can either reduce the time scale and then the dimension, or the dimension before the time scale, and you'll get similar results.